Both prototypes of America's secret new aircraft were destroyed in testing, and the Pentagon called it a success. 2 prototypes, 2 crashes. Not a single aircraft survived. By every normal rule of aviation development, the project should have been canceled. Instead, the opposite happened. The tests became even more classified, and the results became the foundation of a program that would soon change the way aircraft penetrated heavily defended airspace. What had the engineers discovered before both prototypes were reduced to wreckage? Why did Washington consider an aircraft its own designers called the Hopeless Diamond a technological breakthrough? And what exactly happened over Area 51 that suddenly created an entirely new problem for Soviet radar systems? Stay until the end, because today we're uncovering the secret of Have Blue, a project that appeared to lose everything, yet gave American military aviation something far more valuable than the aircraft themselves. The reason Have Blue appeared had little to do with curiosity inside an aircraft design office. By the middle of the 1970s, American military planners were reaching an uncomfortable conclusion. The traditional method of penetrating enemy air defenses was becoming dangerously expensive. Speed, altitude, and maneuverability could no longer guarantee survival. Radar-guided weapons and increasingly organized air defense networks were changing the basic rules of aerial warfare. One response was a secret DARPA research effort known as Project Harvey. The name came from the invisible rabbit in the American film Harvey, but the military problem behind it was very real. The central question sounded almost impossible. Could an aircraft be made so difficult to detect that enemy radar would find it too late or fail to maintain a reliable track at all? This refers, first of all, to the experience of the Vietnam War. American aircraft had encountered dense networks of radar stations, anti-aircraft artillery, and Soviet-designed surface-to-air missile systems. An aircraft could now be detected long before its crew could visually identify the threat. A strike mission was no longer simply a contest against enemy fighters. It was a fight against an entire ground-based system designed to detect, track, and engage aircraft. An even more disturbing warning came from the Middle East. During the Yom Kippur War, the Israeli Air Force faced a dense air defense environment built in large part around Soviet systems. According to the source material, Israel lost 109 aircraft in less than 20 days. For American analysts, this was no longer just a regional lesson. It was a preview of what a much larger war in Europe might look like. This refers to Washington's greatest concern in the European theater. The Soviet Union was building an integrated air defense system in which radar stations, fighter aircraft, anti-aircraft guns, and missile batteries were intended to operate as parts of a single network. A pilot would no longer be facing one isolated missile site. He would be entering an environment where detection, information transfer, tracking, and weapon guidance were connected. In 1974, the United States Defense Science Board examined the possible consequences of a major conflict with the Warsaw Pact. One projected scenario was deeply troubling. If NATO aircraft suffered losses at a rate comparable to those experienced by Israel during the Yom Kippur War, the available NATO air fleet could be exhausted in roughly 2 weeks. For Cold War planners, this was no longer simply a question of efficiency. It was a question of whether an air campaign could continue at all. This refers to the moment when the problem itself began to change. For decades, aircraft designers had searched for advantages in speed, altitude, range, or maneuverability. Now, the military wanted something fundamentally different. Not merely the ability to escape a missile after launch, but the ability to prevent the air defense system from obtaining a reliable target before the strike. That is why stealth was not born as an exotic experiment created simply to produce an unusual-looking aircraft. It emerged as an attempt to escape a technological trap in which every new generation of air defense systems made conventional penetration more costly. The United States needed an aircraft capable of entering defended airspace, where a traditional strike aircraft might be detected, tracked, and engaged long before reaching its objective. The idea of invisibility was beginning to move from engineering fantasy toward military necessity. After Vietnam and the Yom Kippur War, the American military was no longer debating whether a problem existed. The question had changed. Could an aircraft be built that enemy radar would detect too late? DARPA wanted an answer from the biggest aircraft manufacturers in the country, not from theory alone. That was the beginning of a closed competition known only to a very small circle of specialists. The agency sent secret requests to 5 aircraft manufacturers. They were given 2 blunt questions. What level of radar signature would make an aircraft effectively undetectable? And could such a machine be built with the technology available in the mid-1970s? The responses revealed how doubtful the entire concept still seemed. This refers to General Dynamics, one of America's largest defense contractors. Its specialists believed the better answer was electronic countermeasures, jamming, radar suppression, and defensive systems, rather than radically reshaping the aircraft itself. Discussions with the company were then suspended. DARPA was not looking for another way to blind a radar. It wanted an aircraft that would naturally return as little radar energy as possible. Grumman and Fairchild reacted even more simply. They showed no interest in the request. For companies accustomed to building combat aircraft around clear requirements for speed, range, payload, and maneuverability, the new task may have looked too risky and too uncertain. There was no guaranteed production contract. There was, however, a very real chance of spending time and money on a technology that might not work at all. This refers to Douglas and Northrop. They agreed to continue the studies, and each received $100,000 from DARPA for the initial research. By military aviation standards, that was a modest amount because nobody was yet asking for a finished airplane. The first goal was much more basic. Prove that radar reflections could be reduced enough to change the tactical equation. But the story contained an almost absurd twist. Lockheed, a company with enormous experience in secret aircraft programs, was not included in the original request. The reason was simple. It had not developed a new fighter for roughly a decade, so DARPA did not even approach it. The company that would eventually create the first operational stealth aircraft did not begin the competition as a loser. It did not begin the competition at all. This refers to the moment when the entire program could still have taken a completely different path. Northrop already had a place in the project. Douglas was inside as well, and Lockheed remained outside the door. Nobody yet knew that Skunk Works would soon force its way into the competition and offer a solution that would reshape not only DARPA's program, but the appearance of combat aircraft for decades to come. Lockheed might have remained outside the program entirely if information about the secret research effort had not reached the people inside Skunk Works. Ed Martin, Lockheed's Director of Science and Engineering, and Skunk Works Chief Ben Rich learned about the project. Kelly Johnson, whose name was already associated with some of America's most secret aircraft programs, was also connected to the effort. For Lockheed, missing this opportunity could mean surrendering a technology that might define the future of military aviation. But simply calling DARPA and asking to join was not enough. Lockheed relied on relationships with the Central Intelligence Agency that had been built during earlier classified reconnaissance programs. Through the CIA, company representatives managed to approach the people responsible for the new project. The initial answer, however, was no. This refers to an unusual situation. One of America's most experienced companies in classified aircraft development knew that the government was searching for an entirely new kind of airplane, yet officially had no place in the effort. Lockheed had to convince the customer that its engineers deserved to be heard. There was not even a guarantee that the company would be paid for the work. Eventually, DARPA changed its position. Lockheed was allowed into the competition, but under harsh conditions. Initially, without a government contract and without the research funding already granted to some of its rivals. Skunk Works would have to spend its own money. The company had to prove that it belonged in the program before it could expect serious government support. In 1975, the project moved to the next stage. DARPA formally invited Northrop, Douglas, and Lockheed to participate in the Experimental Survivable Testbed Program, known as XST. Its purpose was to determine how far the radar signature of a future aircraft could actually be reduced. The competition was no longer about theoretical papers. The companies now had to produce real shapes that could be measured at specialized radar test facilities. This refers to the moment when the scale of the technical challenge became obvious, even to experienced aircraft manufacturers. DARPA's required radar signature was so low that engineers at Douglas reached a blunt conclusion. The target might be impossible to achieve. Douglas withdrew from the project. One of America's major aircraft companies chose to step away rather than commit major resources to a requirement its specialists considered unrealistic. After Douglas left, the competition was effectively reduced to two teams, Northrop and Lockheed. Their starting positions, however, were very different. Northrop had been involved from the beginning and had already received government funding for its research. Lockheed had been forced to enter through closed channels, overcome an initial rejection, and begin without the same financial support. Only a short time earlier, DARPA had not even planned to invite Lockheed. Now, Skunk Works stood opposite Northrop in a competition that would test whether an entirely new kind of combat aircraft was technically possible. The irony was difficult to miss. The company that had originally been overlooked was about to present one of the most radical aircraft designs of its era. After Douglas withdrew, the XST program became a direct duel between two teams, Northrop and Lockheed. Both had to solve the same problem, but they approached it from different engineering traditions. The theoretical stage was over. DARPA now wanted physical proof that an aircraft could be made so difficult to detect that existing radar systems would face an entirely new kind of target. For the first phase of XST, each team received roughly $1.5 million. The schedule was extremely tight. Northrop and Lockheed had only 4 months to design and build full-scale test models. These were not flying aircraft yet, but their geometry had to represent the proposed designs with great precision. A mistake in a few surfaces or angles could ruin the entire result. This refers to the unusual nature of the competition. The winner would not be chosen for speed, range, maneuverability, or weapons. The models were placed at specialized radar ranges and illuminated from different directions, while engineers measured how much energy returned to the radar. The weaker the reflection, the closer the design was to DARPA's goal. The tests were conducted at White Sands in New Mexico. The Northrop and Lockheed models shared some obvious features: flat surfaces, sharp transitions, and shapes that looked nothing like conventional aircraft of the period. But their engineering approaches were not identical. Northrop made extensive use of angular surfaces, while Lockheed increasingly focused on predicting exactly where each facet would redirect incoming radar energy. Lockheed even constructed a special test pylon, costing $187,000. The model was raised above the ground so that the test site itself and surrounding objects would interfere as little as possible with the measurements. That was a significant investment for a program that had not yet produced a single flying aircraft. But the competition was now being decided by tiny differences in reflected radar energy, so inaccurate measurements were unacceptable. This refers to the moment when two engineering schools were effectively placed head-to-head. Northrop already had serious experience with low observable research and produced a strong design. Skunk Works had entered the competition later and had been forced to catch up quickly. Lockheed, however, committed itself to an extremely strict geometric logic in which every major surface had to serve the primary purpose of reducing radar return. By the spring of 1976, the first phase had reached its decisive point. DARPA compared the performance of both concepts from different radar aspects and selected Lockheed's proposal for the next stage. For Skunk Works, this was a major victory. The company that had not originally been invited to compete was now authorized to move beyond a static model and build a real flying demonstrator. But Northrop's defeat did not mean that its work had failed. Its engineers continued low observable research in other directions. Their accumulated knowledge contributed to later experimental battlefield surveillance concepts, and that engineering path eventually led Northrop towards something much larger and more ambitious. This refers to one of the most important technological forks in the history of American stealth aviation. After XST, the two companies moved down separate paths, but both continued toward low observable aircraft. Lockheed was given the opportunity to build Have Blue and later transform its technology into the F-117 Nighthawk. Northrop continued its own research line, which years later would help lead to the strategic B-2 Spirit. One secret competition, therefore, helped produce two very different philosophies of stealth aviation. One path led to a compact, sharply faceted strike aircraft intended to penetrate heavily defended airspace. The other eventually produced a giant flying wing designed for strategic missions across enormous distances. Yet in 1976, all of that future still came down to two strange models on a classified test range in New Mexico, and one question: which one would appear weaker on the radar screen? Victory in the first phase of XST gave Lockheed permission to move from static test models to a real aircraft. The second phase received the codename Have Blue. The goal was no longer simply to demonstrate a low radar signature on a test range. Lockheed now had to build two machines that could take off under their own power, complete a flight program, and prove that the new geometry worked outside the laboratory. The financial situation was far from generous. As the program faced budget pressure, Ben Rich secured roughly $10,400,000 from Lockheed management. For a project opening an entirely new direction in combat aviation, that was a very limited amount. Skunk Works therefore worked in its traditional style: reuse available components, simplify anything unrelated to the central objective, and avoid spending money on systems the experiment did not need. This refers to the two demonstrators designated HP-1001 and HP-1002. They were not being built as future production combat aircraft. They had no pressurized cockpit, no full mission system, and no aerial refueling capability. Anything unnecessary was removed because Have Blue had one central job: prove that an aircraft with an exceptionally low radar signature could actually be built and flown. Lockheed reused equipment left over from the C-5 program. That decision saved both time and money by avoiding the need to design every component from scratch. Inside Skunk Works, managers, engineers, test specialists, and low observable experts worked in constant feedback with one another. The aircraft evolved as new calculations, test data, and practical problems appeared. The schedule remained severe. Both aircraft were supposed to be completed by October 1977, but a workers' strike disrupted production at exactly the wrong moment. Progress slowed just as the program was supposed to move toward ground testing. Managers and engineers then stepped into the assembly effort, and the first aircraft was brought to completion in roughly 6 weeks. This refers to the character of the entire Have Blue effort. There was no long sequence of prototypes and no comfortable reserve of time. The team was building an experimental aircraft almost like a flying laboratory instrument, except that this instrument had to accelerate down a runway, leave the ground, and come back safely. Every unnecessary kilogram, every unneeded system, and every delay mattered. Have Blue was much smaller than the later F-117. Its wingspan was about 22.5 feet, and its maximum takeoff weight was around 12,500 pounds. The prototypes were roughly 1/4 the size of the future operational aircraft. The second airframe also received radar-absorbent material, while the first was tested without that coating. But despite its simplicity, Have Blue was not merely a crude mock-up with engines attached. It had to prove several things at once: that an extremely low radar signature could be maintained, that the aircraft could remain controllable, and that the entire concept was worth developing further. Each of those problems was difficult on its own. Have Blue had to solve them together? This refers to the moment when stealth stopped being only a problem of radar reflection calculations. The engineers now had a real aircraft in front of them, with all the compromises, limitations, and risks that came with flight. The two small machines, HP-1001 and HP-1002, had to answer the question on which the entire program depended. Could a shape created for invisibility be turned into a practical flying machine? Up to this point, Have Blue could still be seen as a strange technical experiment, an unusual shape, an extremely low radar signature, and a classified test program. But once the engineers moved from static models to a real aircraft, the central problem became impossible to ignore. The geometry that helped the machine disappear from radar also made it extremely difficult to fly. Lockheed was effectively paying for stealth with aerodynamic stability. A conventional aircraft is shaped so that the airflow itself helps keep the machine predictable and controllable. Have Blue followed a different logic. Its flat surfaces and sharp facets were arranged primarily according to the way radar energy would reflect from the airframe. Where aerodynamics preferred smooth curves, low observability demanded hard angles and carefully oriented surfaces. This refers to the most dangerous characteristic of the entire project. Have Blue was not simply an aircraft with an unusual appearance. It was a machine that constantly tended to move away from stable flight. A small deviation could rapidly develop into a motion that the pilot would have to correct almost immediately. The engineers knew this before the first serious flight tests. One development document described the aircraft in almost mocking terms. The airplane exhibits practically every possible mode of unstable behavior. The only thing it doesn't do is sit on its tail when parked. Behind the joke was a very real problem. Without constant correction, the aircraft could quickly depart from the attitude the pilot wanted. This refers to the fundamental conflict inside Have Blue. The better the aircraft had to look to a radar, the worse it looked from the perspective of conventional aerodynamic stability. The designers deliberately accepted an airframe that lacked the natural stability expected from most aircraft of that era. Now they had to find a way to make such a machine controllable. That intermediary was the flight control computer. It had to continuously monitor the aircraft's attitude and make tiny corrections to the control surfaces faster than a human pilot could recognize and correct every developing deviation. The pilot still commanded the aircraft, but electronics were constantly working between his inputs and the unstable machine. Without that assistance, Have Blue could become almost impossible to control. This was where the real technological risk appeared. If the control system failed or behaved incorrectly, the pilot would not simply be dealing with a malfunction. He would be fighting the basic aerodynamic nature of the airplane itself. The aircraft did not naturally want to settle back into calm, stable flight. It had to be continuously held inside an acceptable envelope. This refers to why the nickname Hopeless Diamond was far more than a clever joke among engineers. They had created a machine that looked excellent on radar test equipment while raising serious questions as an actual airplane. Two opposite goals had collided inside one design: being a good flying machine and being a bad target for radar. Yet that contradiction was also the breakthrough. Lockheed was not trying to make Have Blue comfortable, elegant, or naturally stable. It was trying to prove that electronics could compensate for aerodynamic disadvantages if those disadvantages produced a decisive advantage against enemy air defenses. Traditionally, stability had been built mainly into the airframe itself. Now, part of that responsibility could be handed to a computer. So before the first true flight test, the question was no longer only whether radar could see Have Blue. On that front, the results already looked promising. The more disturbing question was whether a human being could take this machine into the air, keep it under control, and bring it back to the runway while the aircraft demanded constant electronic correction. Only an actual flight could provide the answer. By the time Have Blue was ready to leave the factory, the project was already surrounded by an almost airtight wall of secrecy. The aircraft could not simply be rolled onto an ordinary airfield and tested in full view of outsiders. Its shape alone was enough to reveal that this was not another conventional experimental aircraft. So the next stage of the program was moved to the Nevada desert, where secret machines could be tested far from unwanted eyes. The aircraft was disassembled and loaded aboard a heavy C-5 Galaxy transport. It was carried to the classified test site and reassembled there. For the engineers, this was more than the transportation of a prototype. They were moving a machine whose very existence was not supposed to become public knowledge. This refers to the unusual camouflage applied to Have Blue. The aircraft received an iron-based coating and then a complex scheme using 3 different colors, each applied in several shades. The purpose was not simply conventional camouflage. The pattern was intended to break up the sharp facets of the airframe so that even a distant observer would have difficulty understanding exactly what he was looking at. On the ground, the aircraft looked even stranger than it had on drawings. Its low body, abrupt transitions, and diamond-like plan form made it look like a machine shaped for disappearance rather than graceful flight. But now the people standing beside it were no longer only engineers and radar specialists. A human being was going to have to climb into the cockpit. 2 American test pilots were selected for the program, Bill Park and Major Ken Dyson. They would have to determine whether Have Blue could do in the air what had so far existed only in calculations, models, and ground tests. Park was chosen to take the Hopeless Diamond into the air first, while Dyson served as the second test pilot and as a chase pilot during the program. This refers to the most tense moment before the first flight. Until then, a mistake could still be discovered on a test stand, in a calculation, or during a ground check. Once the aircraft left the runway, the cost of an error changed completely. The pilot would be sitting inside a machine that had deliberately sacrificed natural aerodynamic stability for low observability and depended constantly on its electronic flight control system. The trials were meant to examine more than ordinary handling qualities. Have Blue existed because of stealth, so the aircraft also had to be evaluated under conditions that resembled real detection and tracking. It had to show how difficult it would be to find and follow once it was no longer sitting motionless on a radar range, but actually moving through the sky. The entire program was valued at roughly $35 million. By the standards of developing a new combat aircraft, that was relatively modest, but far more than 2 prototypes was at stake. If Have Blue could fly and confirm its predicted low radar signature, Lockheed would have proof that the same principles could be transferred to a future operational aircraft. This refers to the final hours before the first takeoff. The aircraft was already in Nevada, the control system was ready, the pilots knew their tasks, and the engineers could only check once more what they had already checked dozens of times. On paper, Have Blue had already defeated the radar. Now, the hopeless diamond had to prove something much simpler and, at the same time, much more frightening: that it could actually take off and remain in the sky. On December 1, 1977, the moment finally arrived for which the Skunk Works team had endured calculations, static models, classified test ranges, and months of uncertainty. At the secret facility in Nevada, Have Blue moved onto the runway. Bill Park was in the cockpit. The aircraft its own engineers had called the Hopeless Diamond was about to prove for the first time that it could do more than deceive radar. It had to prove that it could actually fly. Park advanced the throttles, and the strange aircraft began its takeoff roll. The angular airframe accelerated along the runway at Area 51, the same isolated location used for some of America's most secret aviation programs. Then, Have Blue lifted from the ground. There was no immediate departure from controlled flight and no desperate struggle seconds after takeoff. The Hopeless Diamond was flying. This refers to the first real victory of the program. Until then, Lockheed could present radar signature measurements, engineering calculations, and flight control data, but only an actual flight could prove that all of those technologies could function together inside one aircraft with a human pilot in the cockpit. The test was not conducted alone. Ken Dyson followed Have Blue in an F-15 Eagle. The fighter served as a chase aircraft, allowing another pilot to observe the experimental machine from outside and provide assistance if something went wrong. The contrast was almost symbolic. One of the most formidable conventional fighters of its generation, flying beside a small, angular aircraft built according to an entirely different set of priorities. On January 17, 1978, the roles were reversed. Ken Dyson took control of Have Blue, while Bill Park performed the chase mission. Only those two men would fly the first prototype. For a program this deeply classified, the number of people who actually knew how the strange aircraft behaved in the air remained extremely small. This refers to an important feature of the Have Blue test program. After groups of flights, engineers studied the data and made small changes to the aircraft and its systems. This was not a finished airplane simply being checked against a fixed list. Every flight was also an experiment, and every experiment could lead to another modification before the next takeoff. Gradually, the initial tension began to fade. Have Blue took off, completed its assignments, and returned to the base. The flight control system managed the aircraft's inherent instability, and Park and Dyson learned its behavior. A machine that had once existed as a dangerous engineering hypothesis was beginning to look like a functioning aircraft. This refers to the psychological change inside the program as well. Every successful flight strengthened the belief that Skunk Works had not gone too far by sacrificing conventional aerodynamic stability for low observability. The simple fact that such an aircraft could repeatedly be flown already mattered enormously. At the same time, the team continued evaluating the characteristic for which Have Blue had been created in the first place: its ability to remain an extremely difficult radar target. Week after week, the flight count increased. Park and Dyson became more familiar with the aircraft. Engineers corrected smaller problems, and nothing occurred that forced the program to abandon the concept. The most dangerous stage of the experiment seemed to be passing. Lockheed appeared to have achieved something that some specialists had considered nearly impossible only a few years earlier. But flight testing follows a brutal rule. Dozens of successful sorties do not guarantee the next one. Have Blue completed its early flights, then passed through the second group and the third. Again and again, the aircraft returned safely to its secret base in Nevada. 35 flights gave little reason to believe that the hopeless diamond was doomed. On May 4, 1978, Bill Park took Have Blue into the air for the 36th test flight. At first, nothing made this mission look different from the ones before it. The trouble began only when Have Blue returned to the airfield and started its landing approach. On May 4, 1978, Have Blue's 36th flight was approaching its end. Bill Park returned to the airfield and began what should have been a normal landing approach. Up to that point, the aircraft had behaved predictably. The problem appeared when it was time to extend the landing gear. During the approach, it became clear that the system had not deployed correctly. The nose gear came down, one main gear extended, but the other main gear remained retracted. For an aircraft with Have Blue's unusual geometry, that created an extremely dangerous situation. A normal landing was now almost impossible. Park went around and tried again to get the system into a usable configuration. This refers to the moment when a routine test flight became a fight over a rapidly shrinking number of options. Ken Dyson was nearby in the chase aircraft and could see the situation from outside. He later recalled that just before touchdown, Have Blue suddenly pitched sharply upward and appeared to strike the runway very hard. Park got the aircraft airborne again and continued trying to extend the gear. Time was now working against him. Every additional circuit consumed fuel, while the landing gear problem remained. Park kept testing the system, but he could not obtain a normal gear configuration. The aircraft was still controllable, but the number of possible solutions was disappearing. This refers to the exchange between the two pilots. Dyson later described the situation in simple terms. I advised him to climb to 10,000 feet for ejection. At that point, the priority was no longer saving the aircraft. The goal was to give Park enough altitude to leave it safely. He began to climb. But the fuel supply was almost exhausted. As Have Blue gained altitude, the engine began to lose power and falter. Park now faced a failed landing gear system, almost no fuel, and an aircraft that would become even more difficult to control without reliable engine power. There was no time left for another experiment. This refers to the final seconds of the first prototype's flight. Park ejected. Have Blue continued without a pilot, descended, and was completely destroyed when it hit the ground. The first hopeless diamond, the aircraft that only months earlier had seemed almost impossible to fly, ended its career on its 36th test flight. Park survived, but leaving the aircraft came at a serious cost. He suffered significant injuries, including a concussion. The consequences of the ejection ultimately ended his career as a test pilot. The man who had been the first to take Have Blue into the air would never return to flight testing. This refers to the human side of the program. Until that day, Have Blue had existed mainly as calculations, radar return diagrams, geometric solutions, and classified reports. Now the project had imposed a real cost on the person inside the cockpit. An experimental aircraft could be rebuilt. A test pilot's career could not simply be restored. Yet the accident did not destroy the Have Blue concept. The first prototype was gone, but the program continued. Lockheed was already close to completing the second aircraft, HP-1002, incorporating improvements based on the experience of the first machine. After the 36th flight, the question had changed. Could the second diamond prove that the accident was a specific technical failure rather than a verdict on the entire stealth concept? The loss of the first Have Blue did not stop the program. While the wreckage of HP-1001 already lay in the Nevada desert, Skunk Works was completing the second prototype, HP-1002. It was not a completely new aircraft. but the experience gained from the earlier flights allowed engineers to remove temporary solutions and bring the machine closer to the configuration they actually wanted to test. The second HAV Blue looked cleaner and more deliberate. It was painted gray. The bulky test instrumentation on the nose was removed, and the awkward spin recovery parachute system was eliminated. Those devices had been useful during the early stage, but they also worked against the very characteristic for which the program existed: low observability. This refers to the most important change on HP-1002. The second prototype received radar-absorbent material that had not been applied to the first aircraft. Lockheed now wanted to test HAV Blue not simply as a geometric shape, but as an integrated system in which the faceted airframe, special materials, and electronic flight controls worked together. Radar-absorbent material did not make the aircraft literally invisible. Its purpose was to reduce part of the radar energy that could return to the transmitting antenna after striking the surface. Combined with the faceted geometry, it was intended to lower the aircraft's radar signature even further. After the accident involving the first prototype, the group of available pilots became even smaller. Bill Park did not return to flight testing, so HP-1002 effectively became Ken Dyson's aircraft. He already understood the behavior of HAV Blue, had watched the loss of the first machine from the chase aircraft, and knew how quickly an ordinary technical failure could become critical. This refers to the program's second chance. Lockheed now had an aircraft incorporating lessons from the first series of flights, and a pilot who already knew the character of this highly unstable machine. The engineers had to prove that the first accident had been caused by a specific failure, not by a fundamental flaw in the entire stealth concept. HP-1002 was tested intensively. Each series of flights produced new information about handling, the flight control system, and the aircraft's actual radar signature. For Skunk Works, the purpose of the program had now shifted. The question was no longer whether HAV Blue could leave the ground at all. The first prototype had already answered that. Now the technology had to show repeatability. The aircraft had to take off again and again, complete its test profile, and return to base while preserving its central advantage, an exceptionally low radar signature. That made the second HAV Blue far more important than a simple replacement for the lost aircraft. This refers to the evolution of the entire idea. The first prototype had shown that a radically faceted aircraft could be made to fly. The second had to show that the same machine could be pushed closer to a true stealth system, with shape, coatings, and electronic controls supporting one another. After the loss of HP-1001, Lockheed effectively had one remaining aircraft with which to complete the experimental program. Ken Dyson continued flying it. For a time, everything suggested that the second hopeless diamond might actually carry the project all the way to the end. After the loss of the first prototype, the HAV Blue program did not slow down. The second aircraft was flown intensively, with Ken Dyson gradually expanding the test envelope. Engineers were no longer interested only in whether the machine could remain airborne. They now wanted to see how the stealth geometry, radar-absorbent material, hydraulics, and electronic flight control system worked together under repeated flight conditions. For several weeks, the second prototype returned to base without an event serious enough to stop the program. HP-1002 kept flying, and the data continued to support the central idea behind the aircraft. But HAV Blue still carried one unavoidable weakness. It depended continuously on the correct operation of its control systems. A major failure could turn an already unstable aircraft into an almost uncontrollable one within seconds. This refers to the 50-second test flight of the second prototype. During the mission, hydraulic fluid began leaking. The fluid eventually reached the engine area. A fire developed, and pressure in the hydraulic system started to fall. In a conventional aircraft, that would already have been a serious emergency. In Have Blue, the consequences were even more dangerous. As hydraulic pressure disappeared, the control system became less effective. The aircraft developed violent pitch oscillations, with the nose moving sharply up and down while Dyson fought to keep the machine under control. An aircraft that had always required constant correction was now losing the very system that made those corrections possible. This refers to the exact danger the engineers had feared before Have Blue ever flew. The aircraft could be extremely difficult for radar to detect, but its aerodynamic instability meant that a serious control system failure gave the pilot very little time. Dyson continued fighting the oscillations as long as he could. Eventually, it became clear that the aircraft could no longer be recovered to normal flight. Ken Dyson ejected. He reached the ground safely, but the second Have Blue was lost. Lockheed now had none of the two demonstrators it had built. The first had been destroyed after a landing gear failure. The second was lost after a hydraulic leak, fire, and loss of effective control. This refers to the moment that could have looked like total failure on paper. 2 aircraft built, 2 aircraft lost. Not a single example survived even as a test machine. If the program were judged only by the physical fate of its aircraft, the result looked devastating. DARPA, however, judged Have Blue by a different standard. The purpose of the program had never been to deliver those 2 prototypes to an operational squadron or keep them flying for years. They existed to prove that an aircraft with a radically reduced radar signature could be designed, built, flown, and tested in the real world. Both machines had already accomplished that before they were lost. This refers to the paradox that defined the entire program. Have Blue lost 100% of the aircraft it produced and still delivered exactly the information its designers needed? The flights validated the basic combination of faceted geometry, special materials, and computer-assisted control. Stealth was no longer just a theory. It had become a technology that could be transferred to a full-scale combat aircraft. That is why the program did not end with the loss of the second prototype. The results were instead judged a major success. Both hopeless diamonds were gone, but their most important achievement survived in test data, engineering reports, and the experience accumulated inside Skunk Works. Lockheed could now move to the next step, building an aircraft that would no longer be merely an experiment, but an operational machine based on the same principles. When the second Have Blue disappeared into the Nevada desert, Lockheed no longer had a single flying prototype, but by then, the central purpose of the program had already been achieved. The engineers had proved that an aircraft with a radically reduced radar signature could be designed, built, flown, and tested in the real world. For DARPA, that was enough not to end the experiment, but to turn it into a much more serious next step. The new effort evolved toward what would become the Nighthawk. Skunk Works now had to take everything learned from the 2 small Have Blue demonstrators and transfer it into a full-scale combat aircraft. It had to be larger, more reliable, powered by 2 engines, capable of carrying weapons, and able to perform real strike missions. The experimental diamond was becoming the foundation of an aircraft intended to penetrate dense air defenses and attack before the enemy fully understood where the threat had come from. This refers to the most important legacy of Have Blue. The future F-117 inherited its basic stealth philosophy: faceted geometry, carefully controlled radar reflections, special materials, and constant assistance from an electronic flight control system. What had looked like an extreme compromise on the prototype was now becoming the basis of an operational combat design. The new aircraft was developed by the same Skunk Works organization under intense secrecy. The future F-117 made its first flight at Groom Lake, Nevada in 1981. But the existence of the aircraft and the results of the classified program remained officially hidden for years. The public did not receive confirmation until 1988, when concealing an entirely new combat aircraft was becoming increasingly difficult. This refers to a rare case in which an experimental technology moved relatively quickly from a secret test range into real operations. The F-117 was not designed as a traditional fighter for air-to-air combat. Its main purpose was different: penetrate heavily defended airspace, reach important targets, and deliver precision weapons while minimizing the enemy's ability to detect and track the aircraft by radar. The Nighthawk gained worldwide fame during the Gulf War. Its appearance, which had only recently been hidden behind layers of secrecy, became one of the symbols of a new era of aerial warfare. Stealth was no longer a laboratory graph or a pair of experimental airframes. It had become an operational capability used against real targets. This refers to the next important stage as well. The F-117 later took part in NATO operations over Yugoslavia, where one aircraft was lost in combat. That episode demonstrated an important truth. Stealth did not mean literal invisibility, and it did not make an aircraft invulnerable. Low observability reduced the probability of detection and engagement, but it could not eliminate enemy tactics, predictable routes, operational mistakes, or the capabilities of a well-organized air defense system. The Nighthawk was later used in the Iraq War. By then, technologies that had seemed almost fantastic during the Have Blue era were becoming part of a much broader American approach to combat aviation. Later aircraft would use more advanced shapes, computing systems, and materials, but the central logic remained the same. An aircraft does not always have to outrun every missile if it can make itself far more difficult for the enemy's sensors to acquire in the first place. This refers to the moment when the history of Have Blue finally moves beyond the two prototypes that were destroyed. The F-117 was officially retired in 2008, but individual aircraft continued to be preserved and were later seen flying during test and training activities. Even after its frontline service ended, the type remained useful for exercises, evaluations, and work involving low observable targets. Yet the most important legacy of the program cannot be placed in a museum. Both Have Blue aircraft were lost, and neither survived as a complete airframe. Their technology, however, outlived the metal from which they were built. It passed through the F-117 and continued into later generations of stealth combat aircraft. That is how the story of the Hopeless Diamond ended. It was an aircraft doubted by some of its own engineers, lost twice in testing, and still able to accomplish its mission completely. Have Blue vanished physically, but its wreckage became part of the foundation of a new era, one in which an aircraft's most important weapon could be not only speed, altitude, or firepower, but the ability to remain difficult to detect until the moment of attack. If you enjoyed the story of the Hopeless Diamond, support this video with a like. Subscribe to the channel for more stories about secret aircraft, forgotten projects, and technologies that changed military aviation. And turn on notifications so you don't miss the next episode. There are still many machines ahead whose very existence was once classified.